Okay, so here is the physics lecture for Friday. So we're doing rotational motion, or at least the tendency to rotate things. And what we've looked in class so far is at what we would call dynamics. So we apply a torque, and the torques are not summing up to zero, so you get an angular acceleration. This is a whole other class of problems, and they are in the area of statics. We've talked about statics before, but we've limited ourselves to where all the forces go through one point. So if you look at the test problems, we had two wires holding a third mass, and they all went through a single point. Now what we can do once we take into account torques is we can look at a situation as follows. So we're going to have like a beam. We're going to support the beam at two locations. And where you're going to have the beam is going to have some weight to it. And we're also going to load the beam. It means we're going to put some masses on here. And we'll start off with something reasonably simple. We'll start off with a beam, and we'll start off with some kind of a mass. So let's specify, let's call this 1. So M1 is 4 kilograms, 4.0 kilograms. And let's say the mass of the beam is 6 kilograms. Now typically if we have a uniform beam, we can, instead of distributing the mass equally along the beam, what we do is we talk about let's put it in one place, the equivalent. So what we can do is we can replace the mass of the beam by a single mass at the middle of the beam if it's a uniform beam. So this is kind of the drawing of what's happening. Now I've got this off-centered so that you would think that the load on this support would be greater than the load on this support. And you would be correct. If you didn't have this mass at all, and if these two support places were the same distance from the edges or from the middle, then you'd have the same loading on both of these. Okay, so let's put some dimensions on here. So from the end to the first support, we'll say it's something. We'll say it's from the first support to the middle of the mass. We'll say it's something. We'll give a distance. Let's do the distance between the supports. So that's going to be some number. And there'll be some distance from the second support to the end of the beam. So let's put some numbers in here, just based on what they look like. Let's say this is 2, this is 3, this is 10, and this is 2, because they look fairly symmetric. And we'll make those meters. So if I wanted to, the question is length of the beam. So it's going to be 2 plus 10 plus 2. 3 just locates where the mass is. So the length of the beam is going to be 2 plus 10 plus 2, which is 14 meters. So the middle of the beam is going to be 7 meters from this end point here. So I think that's all we need. Okay, so now we're going to create a free body diagram. So I'm going to replace the beam with just a straight line. And I'm going to put where the support force is, I'm going to put an arrow. So this is my support force. And we'll call this, let's call this support A, and we'll call this support B. So we're going to have FA and FB. B. We're going to have two loads. We're going to have the load due to the mass 1. We're also going to have a load right in the middle that's due to the weight of the beam. So we'll call this F sub A. We'll call this F sub B. We'll call this the weight of the beam. So let's use a small b just because we used a capital B there. So this is the weight of the beam, and this is the weight of mass 1. So these are the forces that are acting on it. You'll see there's no forces acting in the x direction, so we're not going to have to worry about that. That doesn't mean that we never have to worry about that, but in this particular problem, we're not worried about it. Now, what we're going to do is, here's the tricky part. So when you sum the torques, because it's not rotating, it's not like an axis, there's no axis, there's no axle. So we don't really have a natural point to do the sum of the torques around. So the sum of the torques around any point. So it doesn't matter where we sum the torques around. So let's just write out the Newton's laws that apply to this. So because it's not moving up and down, the sum of the forces equals 0 because there's no acceleration. And we're going to sum the torques. Now the question is, where are we summing the torques around? Well, like I said, it doesn't matter. So it's usually, if you have an unknown force, it's best to sum the forces around one of the unknown forces, the support forces. That just makes the solution easier. You could choose any place. You could sum the forces around point B. You could sum the forces around the end of the beam, either end of the beam. You could do it around the middle of the beam. All those are going to be the same result. So I've just chosen this point A. I'm going to say, well, where the force A is applied, we call that 0. That's the sum of the torques around there. Now, because it's not rotating, the sum of the torques also equals 0. So for static problems, the sum of the forces equals 0, the sum of the, in both the x and y directions, and the sum of the torques equals 0. Now, what are the forces? We just know they have to add up to be 0. Well, you come over here and you look at the ones that are pointing in the y direction, which is every one. So we're going to have F sub A, which is pointing in the positive y direction. So if we do this positive y and this positive x, we've got force A pushing up, we've got the weight W1 pushing down, we've got the weight of the beam pushing down, and we got force due to support B pushing up. So that's how you reflect the signs. FA, W1, W2, F sub B are all positive quantities. Well, they're all positive quantities if we have the right direction. So I'm guessing that they're up because it makes sense. If these are pushing down, then these have to be pushing up. But in some cases, you're not sure. So you make a guess of which way it goes. And if you guess wrong, you've got a negative answer. If you guess the right direction, it'll be a positive answer. Okay, now the torque, we've got two things we got to worry about, is how big the torque is and whether it's plus or minus. So before we do that, we need some distances and distances from this point of rotation. So let's go ahead back to this. And so what we're going to do is we're going to base everything on this is the starting point. Now, force A, there's no torque from force A because it goes straight through that point. The moment arm is 0. So the distance from support A and the mass, well, we go 2 meters. Well, here it is, 3 meters. That's what it is, 3 meters. Okay, so that's the distance to weight W1. Then from that same point to the middle of the beam, well, this total distance is 14. To the middle of the beam is 7. So this is 2 to here, so you have to go 5 more to get to the middle of the beam. So the distance from point A, or the center of rotation to the middle of the beam is going to be 5. 5 plus 2 is 7, and then what we'll do is go another 5 to get to here, and then another 2 to get to the end. Okay, so that's the moment arm of this force relative to this point. And then the final distance is from the same thing to the second support force, and we already know what that's 10. It's given exactly, so that's 10 meters. Okay, so our free body diagram is showing the forces, showing where the center of rotation is, and it's giving you the distances. Now the sign. So we're going to have 3 torques. This one, this one, and this one. This one doesn't create a torque. What you do is you think about if you were to put a little hinge right here, or some kind of shaft that you could rotate around, and you looked at each individual force separately, would that cause it to rotate clockwise or counterclockwise? So if I were to hold the beam here, take this force out, and push down, it would cause it to rotate counter or clockwise around that point. So the first torque is going to be negative. The distance is 3 meters, and we have weight W1, which we're going to calculate here in a minute. Okay, so that's the first torque. It's negative because it would tend to push things around. This one also, if I have an axle here and I push down, it's going to cause this thing to want to rotate clockwise, which is negative. So it's going to be negative 5 meters times the weight of the beam. And then the third torque is caused by this force. Well, we're assuming it's going up. So if we rotate it around this point and pushed up, it would push this beam to rotate counterclockwise. So it's going to be plus, the distance is 10 meters, and the value is F sub B. Okay. So you see, if we know the weights of these two things, we can calculate everything except F sub B, and we can solve for that. So let's go ahead and do that. So mass 1 is 4 kilograms, and mass B is 6 kilograms. And wasn't I using a lowercase there? I think I was. I don't know what I did. For beam. Okay, 4 weight is mass times acceleration due to gravity. So I get 39.2 newtons here, and 6 times 9.8 is 58.8. Carry an extra decimal point here. So those are the two weights. Let's put those down. 39.2, because we're summing forces, not masses. Okay, so those are the two forces. So now we can go down here, say 0 is equal to negative 3 times W1, which is 39.2, minus 5 times W sub B, which is 58.8 newtons, plus 10 F sub B. So let's add the first two terms together. 3 times 39.2 and 5 times 58.8. So you get 0 is equal to negative 412. And the units are meters newtons, because the torque, plus 10 meters times F sub B. So if we solve for F sub B, we're going to have, it's going to be 412 meters newtons divided by 10 meters, or 41.2 newtons. So that's the support force B. Now, what I can do is now go back into the sum of the forces in the y direction equals 0. So we have F sub A. W1 is 39.2 newtons. And we have W sub B, which is 58.8 newtons. and then we have plus F sub B, which is going to be plus 41.2. So if you solve for F sub A, we'll have these two together, and then well, if you move them to the other side, it's going to be positive 39.2 plus 58.8 minus 41.2, and you get F sub A is equal to 56.8 newtons. Okay, so that's the answer. We said F sub A should be greater than F sub B because we have this loading weight which is off-centered towards A, so we'd expect A to be heavier. Okay, so that is what we're going to do is part of the lab next week is we will look at a problem. We'll actually physically put together a beam, and we'll put the loads on it. We'll put the weights using the weights that we have, the masses, and we'll use the dimensions to calculate the two support forces, and then we'll measure them using our load force sensor. So let's just see how much time. I may come down. I may come by and do a second one. Yeah, let's do a second one. Then we'll do one in class, so we'll get a lot of practice at this. So let's make a beam up. We'll always assume that the mass of the beam is uniform, so we can concentrate the mass in the middle. What I'm going to do here is we're going to off-center we're not going to have the two supports exactly symmetric. So we'll do that. And then we'll put some masses on here. Let's do 3 masses. So we'll put one here, we'll put one there, we'll put one over here. And then we have to give them some values. So we'll call this 1, this 2, this 3, we'll call this A, we'll call this B. So let's write them down here. M1 is 3 kilograms. M2 is 2 kilograms. M3 is 10 kilograms. And M for the beam is 7 kilograms. Okay, let's put some dimensions on this thing. So let's go with the whole beam length first. So we're going to make this 24 meters. And we'll take the distance from this edge to here, this to there, that to there, that to the end. And it has to add up to 24. So we're going to make that 2. We also need the distance to the supports. So let's put that distance from here, and then we'll do the distance between the supports. Actually, let's do the distance from both ends. You just have to make sure you don't over-specify things. Well, you don't have to worry about that, but I do. Okay, so we're going to say this is 2, this is 4 from the end to here. The distance between these, let's make 7. So that leaves 9. Let's make this one 3. So that's going to be, well, actually let's make that 2. And so that's 7 plus 4 is 11, so that's 13. Okay, so that's, I think that gives everything we need. So we're going to come up with this free body diagram. So we're going to have our beam, which is going to be a straight line. And we're going to have the force due to mass 1. We're going to have force due to mass 2. We're going to have the force due to the weight of the beam. We're going to have the force due to mass 3. There. We're going to have the two support forces. And what we can do is we can go ahead and calculate the weights. So you would take each one of those and multiply by 9.8. So I'll let you do that. This is 29.4. M2 is 2 times 9.8, which is 19.6. This is the weight of the beam, which is 7 times 9.8. So that's 68.6. These are all newtons. And then there's the final mass, which is 10. 10 times 9.8, which is 90. So that's 90 newtons. This is F sub A. This is F sub B. Now, just to be different, I'm going to rotate around this unknown, just to show you how it works differently. So we need the distances from here to each one of these things, each one of these different points. So I don't think we wrote what this was. What did I say? I didn't say 7. Okay. So it's 4 meters from the end. What that means is this is going to be 11. No, it's going to be 13. Between here, it's 13. So you just gotta do a little math here. So we want the distance from here to here. So we got 7 meters from here to the end and 2 meters from the end to here. So the distance, this distance here, let me use one of these double arrow. So this distance, and this is not quite to scale, so this is 7 minus 2, which is 5. Okay, so that's that distance from here to there. We need the distance from here to the middle of the beam. We need the distance from here to the force mass 2. We need the distance from here to the support force, and we need the distance from here to the mass 1. Okay, so from the middle of the beam is 12 meters. So it's 12 meters from here to the end. It's 7 meters from there to the support. So this one is going to be 5 meters as well. Like I said, it's not to scale. Does that make sense? 7 minus 2 is 5. And so if you think about it, we do 5 plus 5 plus 2 gives you 12. So that adds up. It's a check. Now we need the distance from here to the support. So there's 11 from the ends, so the in-between has to be 24 minus 11, which is 13. So it's 13 meters between these 2 points. Oh, and I forgot this one. Oh, actually, this one is 5. So to the middle, it's 5. 5 plus 5 plus 2. So what are we doing next? We're doing this one here. Okay, so you've got 15 to the end, and then 7 back in, so that's going to be 8 meters. So we start here, 15 minus 7 gives you 8 net. And then we've got the distance from here to there. So how do we do that? Well, we've got 7 meters here. So from here to all the way to the end has to be 24. So if this is 7, this one has to be 17. 17 plus 7 is 24. So this is 17, and then you subtract 2, which is 15. So again, we say from here to the end is the length of the beam, which is 24. So that's from here to here is 17, and from here to here is 2. So the net from here to here is 15. However you want to do that, you just got to figure out these distances. Okay, so now if we do the sum of the forces in the y direction, those equal 0, and we have 4 that are going down. We have minus 29.4, minus 19.6, minus 68.6, minus 90. And then we got 2 forces going upward, which is F sub A and F sub B are 2 support forces. Let's go ahead and add those together. 29.4 plus 19.6 plus 68.6 plus 90. So that's 0 is equal to negative 207.6 plus F sub A plus F sub B. Okay, so that's the sum of the forces, and then you got the sum of the torques around some point, at any point, and I chose that one there. So we're going to have this support force here, F sub B, is not going to give us any torque because we go right through our chosen center of rotation. So this one's we're going to get one from here, one from there, one from there, one from there, one from there. So we got 5 torques. So let's just start on this side. This one, relative to this point, is going to cause this thing to go, it's going to cause it to rotate clockwise. Let's just go ahead and do all of them. Now this one is going to cause it to rotate counterclockwise. This one the same way, counterclockwise. This one's counterclockwise. This one is clockwise. So push down, it's going to go this way. Push down, relative to here, it's going to go that way. Push down, push down. This one pushing up makes it go the other way around. So what we're going to have is this one's going to cause, it's clockwise, so it's negative. This one is counterclockwise, so it's positive. Counterclockwise, positive. Counterclockwise, positive. Clockwise is negative. So those are all the signs. So we'll start with this one. We've got a distance of 5 meters, and we've got 90 newtons, and it is negative. Okay, this doesn't cause torque. This one is positive. The distance is 5 meters. And the force is 68.6. Okay, come down here, or you can keep going if you have more room in your paper. We've got this one. So the distance from here to there is 8 meters. And we have 19.6 newtons. And it's positive because it's counterclockwise. The next one is the support force, so that's going to be negative because it's negative, and the distance is 13 meters times the unknown force F sub A, and then finally this one, which is positive, the distance is 15 meters times 29.4. Okay, so let's add all the stuff not involving F sub A together. So you're going to have negative 5 times 90 plus 5 times 68.6 plus 8 times 19.6, and then skip over the next term, plus 15 times 29.4. So I get 490.8 minus 13 F sub A equals 0, or F sub A is equal to 490.8 divided by 13. And I get 37.8 newtons. And then you can go to the sum of the forces in the y direction. So you'd have 0 equals negative 207.6 plus 37.8 plus f sub b equals 0. So if you take 37.8, subtract 207.6, and solve for f sub b. So this will be negative 170. But when it goes to the other side, it becomes positive 170. Okay. So you see the support f sub b is significantly more than f sub a. And why is that? Well, because you've got this big, heavy mass. Also because this is not centered, or relative, it's not symmetric towards the end. And so I would have expected f sub b to be more so. And if I had made this even larger, at some point this would actually become negative, and you'd have to hold this down instead of holding it up, pushing it up. You'd actually have to have a thing pulling it down to keep it in balance. Now I could have rotated around this point, and I would have gotten the same answers. I would have solved for f sub b first, and then used the same y direction stuff to find f sub a. Now again, if I'd gotten a negative result, if I'd really put an even bigger mass on this side, and this was negative, that would tell me that my assumed direction, which was pushing up, is wrong, that it was actually pushing down. So we'll go through a lab where we'll get practice of doing this again, so it's not the last time you see it. Okay. Now the other kind of problem that I want you to be able to do is the following scenario. So you got a wall, and attached to the wall you have a beam. So let's find my beam. Here we go. So here's the beam. Now one thing about these problems is the question is how are they attached? And that's a little bit beyond the scope of this. So there are different ways of attaching things. You can use a pin. You can use a roller. What we do here is we'd use a pin. What that would mean, so there'd be something sticking out here like some kind of bracket, and you'd have a hole in the bracket, and you have a hole in the beam, and you'd stick a bolt through there so that this thing could rotate. But rotating means that what that means is from a reaction force here at the wall, you can have both an x component and a y component. So we have r sub x and r sub y. Now I know that I'm going to have to push up here to support the beam and anything else that's happening. What I'm going to do is stick on one mass somewhere out here. So I'm going to put it right here, so just like before, except instead of keeping this thing from collapsing, instead of putting a support underneath, what I'm going to do is I'm going to attach a wire right here, and I'm going to then take that wire and attach it to the wall, and this is going to have some angle, say 40 degrees with respect to the horizontal. And let's give some dimensions. Again, we need dimensions. So from the wall to the mass, we'll say is 4 meters. And from the wall to the support is, let's make it 9 meters. And then the length of the whole beam will make 10 meters. And we'll say that this is mass 1, and M1 is equal to 5 kilograms. I should have made them all 0.0, but and then we got the mass of the beam, which is going to be 10 kilograms. Okay, so I've got everything specified that I need to. And the question is, what's the tension in the cable, and what are the X and Y reaction forces? Now, if I had taken this thing and I had just taken a wire straight up, then I wouldn't need this R sub X, because the only forces I'd have would be going down, the weight of the beam would be going down, this would be pulling up, so everything's in the Y direction and you wouldn't need that. But because I've got this wire at an angle, I'm going to have a force, an X component of force and a Y component of force. So that this one involves some of the forces in the X and Y direction plus the sum of the torques. So let's draw our free body diagram on this beam. So here's our beam, which is going to show it as a horizontal line. So we're going to have, I'm going to assume that the reaction force is pushing to the right. That's going to counteract the wire pulling to the left. So that's R sub X. That's R sub Y. We've got this thing's 4 meters from the wall. So we're going to have the weight. This is the weight W1. And then we're going to, one meter from there, we're going to have the weight of the beam. And that's because the length of the beam is 10 meters. So half the length is 5 meters. So the middle of the beam would be here. And this thing's going to be slightly to the left. And then we have the tension, which is going like this. Now, the part that's sticking out here, we don't have to worry about. That's all being lumped into the beam, the weight of the beam. So now we need some dimensions. We need two things. We need dimensions, and we need to figure out where we're going to take some of the torques around. So we're going to take the distance from the wall to the first, to mass 1. We're going to take the distance from the wall to the middle of the beam. Take the distance from the wall to where the wire is. So if we go back and look at this, you can see this is 4 meters. This is 9 meters from the wall to the location. We have an extra meter here that's to the right of the support wire. And then the middle is 5 meters because the total length of the beam is 10 meters. So the distance to the middle of the beam is 5 meters. So again, we're taking the weight of the beam and we're concentrating that in the middle of the beam. So that's our free body diagram. Now, just like we did in our previous experience, we took anything that was in an angle and we broke it into two components. So what we have is we have the Y component of the tension and we have the X component of the tension, and we replace this single tension with the components of the tension. And this angle is 40 degrees. Now, this is the proper way to draw the vectors, because the vector here is, actually it might even be better to put it, better put this one over here and get it over here. That it's pushing at this point, because that's where the wire is attached. So you have this vector pushing from right to left, and this one's pushing up. So I guess it might even be better to do that. So here we have you can think of this as something being pulled, or you can think of it being pushed. It's the equivalent result. So however you want to put the vectors in there, to actually do the triangle, it's better to just do it that way, to make a right triangle. Because if I leave it here, it doesn't look like a right triangle, but if I move it over here, it does. I've just got to remember that the distance that I use for this, to this vector, is from here to there, not from where I drew it on the board. So that's the disadvantage. So really, it's best to leave it that way. But we know that this is the side adjacent to the angle. So t sub x is going to be equal to t times the cosine of 40 degrees. And t sub y, as a consequence, is going to be t times the sine of 40 degrees. Okay, so we have now what we can do is we can do all three equations. Sum of the forces in the x, which is 0 because it's not moving. Sum of the forces in the y equals 0 because it's not moving in that direction either. And the sum of the torques around some point equals 0 because it's not rotating. Now, we're going to choose that point. And the reason we're choosing that point is because both r sub x and r sub y go straight through that point, and therefore these two don't contribute any torque. So when I do this, and also t sub x doesn't contribute any torque because if you extend this, it goes straight through that point. Only t sub y is going to cause a torque. Neither of these because they're right on that point, and this one because it goes straight through that point. It's kind of, if you think about it, it's kind of like if you have a wheel. So there's two situations where you don't create any torque. You could push on the middle of the wheel like that, or you could push straight into the wheel. And if you extend this vector, it's going to go straight through the middle. So that one's not going to cause a torque, whereas this one is going to cause a torque. So it's kind of the same thing, except we're not dealing with round objects here. Okay, so let's see what we got in the y direction. Now the forces don't disappear because they exist, it's just the torques don't exist because of those. Okay, so we're going to have positive r sub y. We're going to have minus W1. We're going to have minus the weight of the beam. And we're going to have plus T sub y. Okay, and that equals 0. Secondly, that's actually, that's the y direction. So let me move this down here. Okay, that's the y direction. In the x direction, I've got positive r sub x and negative ty. So you got push. This one's pushing to the right. This one's pulling to the left. And then the torques. So again, these don't contribute. So what we're going to have is we're going to have 4 meters. I'll put in the weights first, and then we'll plug them in a second. So the distance from this point of rotation to the first mass, to the only mass, point mass, is going to be 4 meters times W1, and because this would cause a rotation clockwise, it's going to be negative. This one's also going to cause a clockwise rotation about this point, so it's also negative. So that's 5 meters times the weight of the beam. And this one causes it to rotate around this point counterclockwise, so that's going to be 9 meters times T sub y. Okay, so let's take those three and plug in what we know. Well, first one, there's nothing we can stick in there, so we'll just leave that the way it is. Second one, we've got r sub y minus W1, which, what is W1? I've got to calculate that because we're given the masses, right? So let's go here. W1 and W2. We know this one is 998 newtons because 10 times 9.8. So this one's going to be 49 newtons, half as much. Okay, 49 and 98. So let's go back over here. So 49. Did I get those in the right order? 49 and 98, yep. Minus 49 minus 98 plus T sub y equals 0. So we got two unknowns, but now if we go to the last one here, we're going to have negative 4 times W1, which is 49. So we don't put negative 49 because this is reflecting the direction in the terms of the y direction, but the weight is positive. Then we have minus 5 times 98 plus 9 times t sub y. Okay, so we're going to have the first two terms are negative. 4 times 49 plus 5 times 98. So you add those first two terms together, you get negative 686 plus 9 t sub y. T sub y equals 686 divided by 9, which is 76.2 newtons. Okay, so that's t sub y, and that's usually what happens is you can solve for t sub y through the sum of the torques. You can see how the sum of the torques is kind of the go-to first formula. It's the one that allows us to solve with judicious selection of the point of rotation directly. So in some ways, this is easier than the ones we've been doing before. You know, when we had to, sometimes we had two equations and two unknowns. Here, we have one equation and one unknown. We can solve for that, and then we can just substitute in. So now that we know t sub y, we can plug that in to the sum of the forces in the y direction. So that's 76.2. So if we add all the constants together there, 49, 98, you'll get negative 70.8 newtons, or r sub y is 70.8 newtons. Okay, so that's r sub y. We got t sub y, r sub y. Now, how the heck do we get r sub x and t sub x? Well, so what we're going to do is find t sub x, and then once we have t sub x, we can find r sub x. So the deal there is, if you go back to the force triangle for the tension, you got this scenario. You got 40 degrees. Reminds me, did I put 40 degrees in here somewhere? I don't need to. No, I don't need to know that yet. Okay, I haven't used that yet, have I? So this is t. This is t sub y. This is t sub x. So what I know from my sum of the torques is that t sub y was 76.2 newtons. So trigonometry says that the sine of theta is the opposite over the hypotenuse. Cosine of theta is the adjacent over the hypotenuse. And the tangent of theta is equal to the opposite over the adjacent. So this is the three main trig functions. Well, if you look here, which one can I use? Well, I know t sub y, and I know theta, right? So the tangent of 40 is going to be 76.2 divided by t sub x, or t sub x equals 76.2 divided by the tangent of 40. So 76.2 divided by the tangent of 40, and I get 90.8 newtons. So that's t sub x, and you can also get t by using either one of these now. So if we solve for t, like I said, doesn't matter. Here would be t sub y divided by the sine of theta. So t sub y is 76.2 newtons divided by the sine of 40 degrees. And I get 119 newtons. You could also do it the other way. You could take t sub x divided by the cosine of theta. So that would be 90.8 divided by the cosine of 40 degrees. We should get the same answer. Divided by the cosine of 40 degrees. You get 119 newtons. Okay, so whichever one you want to use. So now we know T. It's 119 newtons. We know T sub x is 90.8 newtons. And now that we know T sub x, we can solve for R sub x. So let's just put that in here. So from sum of the forces in the x direction, it says T sub x equals R sub x. So R sub x is equal to 90.8 newtons, which is positive, so we guess the right direction. So if you think about that, those support forces, you would get this kind of arrangement. You get R sub x equals 90.8 newtons, and R sub y is equal to, I forgot what it is already, was 70.8 newtons. Now, again, to make this into a nice right triangle, I'd move that up here, which you can do. You can do with vectors. So that's that. That's that. So the resultant support vector is actually this. Oops. Is this vector, like that. So that's R, and the magnitude of the R vector is equal to the square root of R sub x squared plus R sub y squared. So that's going to be 90.8 squared plus 70.8 squared. And take the square root of that. So I get 115 newtons. R sub, that's just R, magnitude of the R vector. And then you could figure out, let's call that alpha, the angle that makes with the horizontal. Alpha is going to be equal to the inverse tangent of R sub y divided by R sub x. So you have the inverse tangent of R sub y, which is 70.8 divided by 90.8. So you get 38 degrees. Pretty close to the other one. The tension, and it's probably just based on the dimensions that I chose. It doesn't always have to be exactly close to each other. But okay. So the way if you take statics, you'll deal with a lot of this stuff, and the only difference is that you instead of, you just deal with vectors in more of a what we call a unit vector notation scenario. So but it's basically the same. It's a lot of geometry and figuring out what you would do. Is, let me just kind of give you a real rough idea of what you would do, is you would define vectors from your point of rotation to each one of these points. So instead of just saying it was 5 meters, you would say that it was 4 meters in the x direction. And it's positive because you're going from here to here, whereas if I were looking back here, this previous problem where I was rotating around this point, the R vectors would have a negative sign because they would be going from here to the left, which would be negative, and the one going from here to here would be positive. And that's and just generalize it so you can do things in 3 dimensions instead of just 2 dimensions. But the basic concept is true. The basic idea here is you've got 3 equations, which I thought I had them at the beginning. So you've got 3 equations that we're going to be dealing with. Sometimes you only need to use 2 if it's just a flat beam without any wires attached. But the most you've got 3 equations. Sum of the forces in the x equals 0. Again, that's because there's no acceleration. It's no movement. And you got the sum of the forces in the y and the sum of the torques. And the key thing too is that the point of rotation, or the point that you take the sum of the torques around, is irrelevant as far as getting the correct answer. You pick that point to simplify the solution, which usually means that you place that point of rotation at one of the points of unknown load. And that way you don't have to solve simultaneous equations. If you pick some place other than where the load is, say one end of the beam, you'd have to use substitution to solve 2 simultaneous equations. In this case, we don't have to do that. Also, the important thing is determining whether you have positive torque or negative torque, and that all depends upon where you pick your point that you're rotating around, and what would that force and that pivot point do apart from all the other forces acting on it. So you just look at as if there was just one force being applied, and would that cause something to rotate. The reason that the point of rotation doesn't make any difference because it's not really rotating. It's a static object, so it doesn't rotate. Now there are cases where you could some torques. Say if you had a wheel that's rotating, you could sum the torques around some place other than the center of the wheel. And there are some cases where that kind of scenario makes sense, but mostly it makes sense to do them around the point of rotation when it actually is rotating. Okay, so that is statics. On Wednesday we'll do a lab which will give us some more practice at this situation. So I'm going to go ahead and stop. It's about an hour, so hopefully you enjoyed your sleep in.